Hello everyone, this is Professor Ng Chi Kun from Unimas. In this video, I'm going to give you a lecture on inference lines for statically determinate structures. If a structure is subjected to a moving load, the variation of shear and bending moment is best described using the inference line. One can tell at a glance where the moving load should be placed on the structure so that it creates the greatest inference at the specified point. The magnitude of the associated shear, moment or deflection at the point can then be calculated using the ordinates of the inference line diagram. One should be clear of the difference between inference lines and shear or moment diagram. So an inference line will look like a shear or bending moment diagram, but they are different. Inference line represent the effect of a moving load only at a specific point. So in inference lines, the loads are not static. They are moving. Okay, they are moving from the loads are moving from one point to another. But in drawing shear force and bending moment diagram, the forces or moments are static, so they don't move on the structures. Shear or moment diagrams represent the effect of fixed loads at all points along the axis of the member. Okay, so the procedure for analysis, there are two methods. One is by tabulate values, and then the other is inference line equations. So meaning that we write equations of the inference line. So the first method of using tabulate values. So first of all, we will place a unit load at various locations x along the member. So we choose probably 3 or 4 points on a structure or a beam along the length of the member, and then we put a unit load at each location to see what is happening to the reactions, to the shear force, and also to the moment at a specific location. At each location, use statics to determine the value of function or at the specified point. If the inference line of a vertical force reaction at a point on a beam is to be constructed, consider the reaction to be positive at the point when it acts upward on the beam. So meaning that we take upward reaction as positive. Yeah? If a shear or moment inference line is to be drawn for a point, take the shear or moment at the points as positive according to the same sign convention used for drawing shear and bending moment diagram. So in the previous subject, you have already learned about drawing shear force and bending moment diagrams. So over here, we are going to use the positive sign convention that you use also in drawing shear force and bending moment diagram. So any moment that causes an element to bend this way, we call this moment positive bending moment. So on the left hand side of the element, we put the moment as clockwise. If we cut across the section and isolate this part of the structure as a free body diagram. And if we cut across a section and the bending moment is on the right hand side of the cross section, then we put an anti-clockwise moment as the bending moment. So these are all positive bending moments depending on which side of the bending moment that we are considering in the element. And then for shear, we are taking shear that causes the element to deform this way as positive. Yeah. Okay, so this is shear. So we take this as a positive directions for shear. So meaning that if you cut across a section and the section here we have a shear, on the right hand side of the cross section. Yeah? If the cross section is on the left hand side, then the shear will be upward. Yeah? So this is positive shear for this side. This is also positive shear for this side, depending on which side that you cut across the section. So all statically determinate beams will have inference lines that consist of straight line segments. So for statically determinate beams, we will have only linear function or a linear graph as the inference lines. If we want to use inference line equations, okay, if you want to write the equations for the inference line, then the inference line can also be constructed by placing the unit load at a variable position x. So now we don't fix x. Just now in tabulating values, in the method of tabulated values, we fix the load at different points. Okay, meaning that we put the unit load at one point, and then we put another unit load at one point again, and so on and so forth. But in writing inference lines equations, we don't fix the location, but we say that it's a variable position x. So this variable position x on the member, when it is placed, when the unit load is placed on the structure, then we calculate the reaction R, or shear force V, or bending moment M at the point as a function of x. So we don't fix x with a value. Okay, and then the equations of the various line segments composing the inference line can be determined and plotted. So with all the previous description, probably you're still not clear on how to apply all the methods in drawing inference line. So that's why I'm giving you an example here. So in this case, you're asked to construct the inference line for the vertical reaction at A of the beam. Okay, so now we want to draw an inference line for this particular support, which is a pin support with a span of 10 meters. Okay, so as I mentioned just now, we have two methods. One is by using the tabulated values. The other one is by using the inference line equations. Okay, so the method of tabulate values is that we place a unit load, okay, at the certain points of the beams. So in this case, we may divide this beam into 4 similar segments. Okay, so each segment length is 2.5 meters. So we have 1 point, 2 point at the x equals to 5 meter, and then another point is x equals to 7.5 meters. Okay, so in this case, first we'll look at what happened to reaction AY. So this is the force that we're interested in drawing the inference line. Okay, so first of all, we put a 1 unit force at 2.5 meters away from point A, and then just now we said that we want to use upward reaction as positive, so we put a reaction in the upward direction. Okay, so that when we get positive solution, then AY is positive. If we get negative, which is the downward direction, then AY is negative. Okay, so we are just using one direction as positive, that is upward positive. So in this case, with a 1 unit force at 2.5 meters away, then if you sum moment at joint B here, then we take anti-clockwise moment as positive. So sum of moment at joint B is minus AY times 10 plus 1 times 7.5 meters, so equals to 0. So in this case, AY equals to 0.75. And then if the one unit force is acting at 5 meters from joint A, then if you sum moment at joint B, then we have a minus AY times 10 plus 1 times 5 equals to 0, and then AY equals to 0.5. Then next, we put a 1 unit force at 7.5 meters away from this point here, and then you will be getting AY equals to 0.25. So if we tabulate all the values by taking the location of the 1 unit force against AY, okay, so when x equals to 0, AY is equals to 1. This one was not demonstrated here, but if this 1 unit force is at this location here, then AY equals to 1. Okay, even if you sum moment here, if this 1 meter force is over here, then if you sum moment here, then you get AY times 10 equals to 1 times 10. So AY equals to 1. Okay, so x when the location of the force is at the support A, okay, then AY is 1. And then when the 1 unit force is at 2.5 meters away from the support A, then the reaction is 0.75. So these are dimensionless because it's based on 1 unit force, so no kilonewton or no other unit to this force. Right, when the force is at 5 meters away from the support A, then the support reaction at AY is 0.5. And then when it's at 7.5 meters, then the support reaction AY is 0.25. And then when the 1 unit force is acting at joint B, okay, if the 1 unit force is here, there will be no more AY. AY equals to 0 because the 1 unit force is here. Okay, so it does not transmit reactions to AY. Okay, so with all these points, we may plot AY against X. So if you plot AY against X, this will be the line that you can get from all these tabulated values. Okay, so this is an inference line for the support reaction AY. Okay, so this is called an inference line. Okay, for AY. So that when we want to know what happens when 1 unit force is here, then the ordinates will tell you what is the support reaction AY. So this is only at a particular point at AY. Okay. Next, if we want to use the inference line equation, okay, then we may use the reaction as a function of x determined from this free body diagram. So now we don't fix the location of x. Just now in tabulating value, we fix x at 2.5, and then we fix x at 0, 2.5, 5, 7.5, and 10. Okay, but in this case, we just put x as a variable, so the location of x can be anywhere. All right. So with this, then we sum total moment at B. Okay, so what do we get? We get minus AY times 10 plus 1 times 10 minus x. Okay, 1 times 10 minus x, and then we have minus AY times 10. So there is no other moments, then we equate this to 0, And solving for ay, we get ay equals to 1 minus 1 over 10 x. So this is the inference line equation for reaction ay. Right? So once you plot this into a graph, then this line is defined by this equation. Ay is equals to 1 minus 1 over 10 x. So these are the two methods that we may use. One is by tabulating the values, okay, and then the other one is by writing the inference line equations. All right, let's look at another um, example here. Okay, so here you are asked to construct the inference line for the moment at C of the beam. So now we are only interested in the moment at location C. Okay, so I want to see what happens to moment at joint C when one unit load is moving from support A to B. Okay, so the only cross section that we're interested in is section C, right? So section C is at the midspan of the beam. Okay, so if you want to tabulate values, okay, so if you want to tabulate values, so at each selected position of the unit load, the value of MC is calculated using the method of sections. Okay, so first we put 1 unit load at the reaction there. Okay, if we put 1 unit load here, okay, then we cut across section C and see what is the bending moment. Okay, so it's not demonstrated in this particular example here. So let me draw a diagram to indicate that. So this is when x equals to 0. So when x equals 0, this 1 unit force is here. And then this is AY. And then this is BY. So we're only interested in AY. So in this case, when we cut across a section at C, what do we get? We get a free body diagram that looks like this. So in this case, we know that this support reaction AY is also 1. And then this distance is 5 meters. So this point is point C. Okay, so when you cut across the section C, there must be a shear force and bending moment diagram. So as mentioned before, whenever you want to put an unknown force as the shear force or bending moment diagram, we follow the sign convention for positive bending moment and we follow the sign convention for positive shear. Yeah. So as mentioned just now, positive bending moment is like this. So if the bending moment is on the right hand side of the cross section, it is anti-clockwise. If the shear is on the right hand side of the cross section, it's downward. Okay, so meaning that this bending moment is anti-clockwise, which is positive, and then this shear is downward on the right hand side of the cross section, so it's also positive shear. Right? So in this case, if the 1 unit force is here, then AY is equals to 1. Okay, so if you sum moment here, okay, then 1 times 5 might we have 1 times 5 minus AY times 5 equals to 0. AY is 1, so we get M equals to 0. Okay, when we sum moment, then we have m plus 1 times phi minus 1 times phi equals 0, then m equals to 0. So in this case, m equals 0 when x equals 0. So mc is 0. So this is mc. Right? This bending moment is mc because it's at point C. Yeah? Okay? Alright? And then the second location that we choose is at 2.5 meters away. So when this is at 2.5 meters away, just now we have already looked at the previous example. The reaction here is 0.75. Okay? So similarly, if we cut across section C here, okay, and isolate this part as a free body diagram, and then we get a free body diagram like this. Okay, so why this shear force is upward and why this MC is clockwise as opposed to this? Because this shear force and bending moment MC here, they are on the left hand side of the cross section. This one is on the right hand side of the cross section. So on the left hand side of the cross section, if you look at the positive sign convention of the bending moment and shear force, so the bending moment should be clockwise and shear force should be upward for the positive sign conventions for bending moment and as well as shear force. Okay, so in this case we have a positive bending moment that is going in clockwise direction, and a shear force that is going up, which represent positive shear force also. Alright, so now we can sum moment at joint C. So when we sum moment at joint C, then we have minus MC plus 0.25 times 5 equals to 0. So MC is equals to 1.25. So when X is at 2.5 meter, then MC is 1.25. Right? And then next, if we move on to the other location when X equals to 5, okay, so if this force is at 5 meters, so if this force has already moved to 5 meter here, so there's no more force here, so this 1 unit force is at 5 meter. Okay, so this is 1 unit force. So in this case, this support reactions become 0.5, and this support reaction also becomes 0.5. Okay, so if you cut across section C also, so if you cut across section C, we'll see something like this also. But now the support reaction at B is 0.5. Okay, so in this case, when we sum moment at joint C here, and then we have minus MC plus 0.5 times 5. So MC is equals to 2.5. Okay. Alright, so when X is equals to 5, then MC is 2.5. Okay, and then we move on. We move on to place the 1 unit force at 7.5 meters. Okay, so now we move on to place this force here, move it to 7.5 meters. So this is still 1 unit force, and then there's no more force here. So this is at 7.5 meters. Okay, so if the 1 unit force is at 7.5 meters, so then this reaction will be 0.25, and then this reaction will be 0.75. Okay, so in this case, it's easier if we cut across a section C here and isolate this part of the free body diagram as this part as free body diagram, because the 1 unit force does not appear there. Okay, so we just take this part of the structure as a free body diagram instead of taking this part. Okay, but even if we take this part here, okay, so there is a 1 unit force there. Okay, and then this is 2.5 meter. So this is 2.5 meter, and then this reaction is 0.75. Okay, so even if we use this free body diagram, we may also solve for the bending moment MC, but it's just there's another step further that we have to do because of this 1 unit force here. So let's look at how we sum this moment here and get the solution. So if we sum moment here, then we are going to get minus MC, and then we have this 0.75 meter force at 5 meters away. So this becomes 0.75 times 5, and then we have another term by the 1 kilonewton force. So this 1 kilonewton force has a moment arm of 2.5 meter from joint C here. Okay, and then is a clockwise moment. So clockwise moment is minus. So we have minus 1 times the moment arm, that is 2.5 meter. Okay, so with that, if we solve for MC, then we'll get MC equals to 1.25 or so. Okay, and then alternatively, if you use the other side of the free body diagram, so we have 0.25 here, and then we have VC and MC like this. Okay, so in this case, the 1 kilonewton force does not appear here. See? Okay, so in this case is much easier. Okay, so we have 5 meters here. Okay, so in this case, when we sum moment at joint C, then we have MC minus 0.25 times 5 equals to 0. So MC equals to 1.25. So both ways we get the same answer. Okay, this MC is the same as this MC. Alright, and then if this 1 unit force has moved on to the support there at support B, okay, if the 1 unit force has moved on to support B, okay, what do you get? So now if the force has already moved here at support B, right? It's no more here. This one unit force is normal there, but it is at support B. So this is when X is equals to 10 meter. So when this one unit force is at support B, okay, then support B will have a support reaction of A unit, and the support reaction at A becomes 0. Okay, so in this case, when you cut across at section C, so the one unit force is here. Okay, this is 1, this is also 1. Okay, so when you sum moment, then you have minus MC minus 1 times 5 plus 1 times 5 equals to 0. So MC equals to 0. So MC equals to 0. Okay, when X equals to 10. So you plot all these tabulated values with respect to the x-axis, okay, and MC are the ordinates. Okay, this is MC. So this is when the one unit force is at x equals 0. This is at x equals to 2.5. This is x equals to 5, and then x equals to 7.5, and x equals to 10. So this may look like a bending moment diagram, but it's not bending moment diagram. This is an inference line for bending moment at point C. Okay, right? So this is the inference line for MC, the bending moment at joint C, because we always cut across the section at C to get MC, right? Only the loads and only the one unit load is moving. Okay, this point C does not move. It's always at the midspan of the structure. So next, if you want to draw the inference line equations for MC, okay, so in this case we have two segments of the inference line. Okay, so one segment is when you cut across section C, the one unit force is still there. Okay, and if this one unit force has moved beyond 5 meters, then if you cut across this section here, the one unit force is on the other part of the free body diagram, but it does not appear on this free body diagram. Okay, and then the support reactions, we have already done the equation in the previous example. So AY is equals to 1 minus 1 over 10 x. Okay, so this is similar. This one, this is a similar beam to the previous example. So AY, the support reaction AY has been solved, and the support reaction is given in this equation here. Okay, so first of all, we look at when X is 5 meter or less. Okay, so we look at when X is 5 meters or less. So from 0 to 5 meters. Okay, then the free body diagram will look like this, where the one unit force is still appearing in the free body diagram. So in this case, if we sum moment MC, okay, so you sum total moment at MC, then we have minus, oh sorry, should be plus, because this is the anti-clockwise moment, so positive MC plus 1 minus, oh sorry, it's not minus, it's MC plus 1 times 5 minus x. So the moment arm of this one unit force is 5 minus x. Okay, and then we have this force which causes clockwise moment about point C. So we have minus AY times 5. So minus of this AY times 5, and then this is equals to 0. So solving for MC, MC is in this manner. MC is 1 over 2 x, right? So this is the inference line equation for x equals to 0 to 5 meters, right? And then when x is greater than 5 meter and smaller than 10 meter, so meaning that this 1 unit force have moved beyond point C, yeah? Okay, so when it moves beyond point C, in this cross section you don't see the 1 unit force here already, it's on the other side, okay, of the free body diagram. Okay, so if we sum moment at joint C here, then we have MC minus AY times 5 equals 0. So MC minus AY times 5 equals 0. So we get MC equals to 5 minus 1 over 2 x. So this is for x of 5 meters to 10 meters. Okay. So when x is equal to 0 to 5, then MC is half x. Okay. And then when x is 5 to 10 meters, then MC is 5 minus half x. Okay, as we have solved from here. Okay, so that's all for the lecture today. Thank you very much for watching.